Hidden beyond our Milky Way lies a truly bizarre cosmic structure. Not long ago, astronomers identified a region in space that doesn't pull in surrounding matter. Instead, it appears to push it away. This mysterious zone, now known as the Dipole Repeller, has since become a major focus of astrophysical research. Surprisingly, its repelling force is believed to be just as powerful as the gravitational pull of the well-known Shapley Attractor. So, what exactly is propelling our galaxy through the cosmos? And what implications does this have for our future in space? Could the Dipole Repeller be defying gravity itself, reversing the very law of gravitational attraction? Stick with us until the end as we dive deep into this fascinating phenomenon. Contrary to being a lone wanderer, the Milky Way is part of a vast, interconnected network of galaxies and clusters, all moving in a complex cosmic dance across the universe. More specifically, the Milky Way is part of an enormous region spanning around 520 million light-years, long identified by scientists as the Laniakea Supercluster. At least, that was the widely accepted view, until a recent discovery began to challenge this classification. But we'll return to that shortly. What remains certain is that our home galaxy, along with the larger local group, isn't standing still. It's racing through space at an astonishing speed of 630 kilometers per second, or about 2 million kilometers per hour. For years, scientists have tried to understand the cause and direction of this immense motion, often pointing to the so-called Shapley Attractor. This is the most massive known concentration of galaxies, located up to 700 million light-years away. Within this vast region, gravitational forces are so intense that they overpower the general expansion of the universe, keeping galaxies within its domain gravitationally bound, rather than drifting apart. Astronomers had long believed that most galaxies and galaxy clusters were being pulled toward a massive, gravity-dense region in space. However, a research team led by Yehuda Hoffman from the Hebrew University of Jerusalem challenged this assumption. They uncovered the presence of completely different cosmic structures that play a major role in shaping the universe's large-scale motion, leading to the discovery of what's now known as the Dipole Repeller. To reach this conclusion, the scientists analyzed the movement of galaxies within our supercluster, using data gathered from multiple telescopes, including the Hubble Space Telescope. From this data, they constructed a comprehensive flow field, a detailed model showing the direction and speed of galactic motion across our cosmic neighborhood. But what they found was unexpected. The flow lines didn't all converge toward the well-known Shapley Attractor. Instead, they noticed that, on the opposite side of the Laniakea region, there lies another distinct area in space exerting an entirely different kind of influence. Experts have observed a surprising clustering of lines that deviates sharply from typical patterns. Unlike areas that usually exert gravitational pull, this cluster displayed a repulsive effect. As Hoffman explained, we discovered that our Milky Way is moving away from a vast, previously unrecognized region of low density in space. The nature of this low-density region becomes more apparent when we consider that the so-called Dipole Repeller lies in an unusually sparse part of the cosmos, with far fewer galaxies and clusters than is typical. What makes this finding especially intriguing is that calculations revealed the Dipole Repeller influences the motion of our local group almost as powerfully as the Shapley Attractor, a massive structure that draws galaxies toward it. Remarkably, both regions contribute nearly equally to the local group's velocity. Researchers highlighted that this marks the first time a repulsive force of this kind has ever been identified in space. What does repulsion really mean in this context? And does the so-called Dipole Repeller actually repel matter in the literal sense? Could anti-gravitational forces be involved here? Not exactly. But let's start from the beginning. On a large scale, two major forces shape the universe, gravity and, on an even grander scale, dark energy. For this discussion, though, only gravity matters. As we know, Gravity is the force through which mass attracts mass. Stars pull on planets and other stars, galaxies draw other galaxies closer, and galaxy clusters can even pull entire groups of galaxies toward them. Regardless of the situation, the rule remains the same: gravity always attracts. In classical physics, there's no such thing as repulsive gravity. So, how do we explain the dipole repeller, which seems to push us away and is often described as a center of repulsion? The key lies not in what this region does, but in what it doesn't do. The area has a very low density and contains very little mass. As a result, it doesn't exert a gravitational pull on us. And because we're not being held by it, it gives the illusion of pushing us away. In reality, it's not repelling us, it's simply failing to attract us. On the opposite side, where the Shapley Attractor lies, there exists an enormous concentration of mass that exerts a strong gravitational pull on us. Since there's no similar gravitational force on the other side to counterbalance it, an imbalance occurs. It's this very imbalance that causes us to drift away from the emptier region and move toward the area with more mass. To better understand this, imagine the universe as a giant elastic rubber sheet. When we place heavy balls onto this sheet, they create dips, representing massive regions with strong gravity. Now, if we place a smaller ball, like our Milky Way, on the sheet, it naturally rolls toward one of those dips, attracted by the mass. But if there's nothing on the other side of the sheet, no dip, no weight, then there's no force holding the ball in place. The smaller ball rolls away from the empty side, not because it's being pushed, but because there's simply nothing pulling it back. Translating this analogy back into cosmic terms, the overall movement away from the void seen in measurements only appears as if something is pushing us, when in reality, it's the lack of gravitational attraction that causes this motion. Astronomers have therefore called this area a repeller to choose an image that describes the observed behavior. In reality, however, the dipole repeller does not repel anything at all but merely does not attract anything, and that is a crucial difference. Despite all this, this discovery is nevertheless of great significance. After all, it shows that the absence of mass also plays an important role in the movement of galaxies. According to this, our Milky Way is not only heading toward massive regions but is also moving away from empty areas. The motion of our local galaxy group is driven by two opposing forces: on one side, a powerful gravitational attractor, and on the other, a vast, nearly empty region that we're essentially being pushed away from. This dynamic creates a dipole-like pattern of movement, with one side pulling us in and the other appearing to push us out. But does the Milky Way truly belong to the Laniakea Supercluster? Beyond that, a deeper question remains: where is our journey through the cosmos ultimately leading, and which massive structure can we truly call our galactic home? For a long time, scientists believed that our local group of galaxies was part of the Laniakea Supercluster, an enormous structure containing roughly 100,000 galaxies. However, recent findings challenge this idea. In the Cosmic Flows 4 project, a research team led by Aurelian Tully at the Leibniz Institute for Astrophysics in Potsdam studied the motion of over 56,000 galaxies. Their goal was to better understand the universe's large-scale structure and, more specifically, to determine how galaxies move and which regions exert a gravitational pull on them. Scientists have now found that our previous understanding of the Laniakea Supercluster may be inaccurate. Instead of a single, unified structure, they identified 17 distinct basins of attraction, gravitational zones where galaxies are drawn together by the pull of massive cosmic structures. One of these zones is the Sloan Great Wall, a colossal assembly of galaxies and among the largest known structures in the universe. What's particularly remarkable is that this region's gravitational reach is more than twice that of the Shapley Supercluster.